Welcome back. In today's video, we are going to talk about what happens when we do not have a uniform cross-sectional area. So to model this, I'm going to draw two spheres, one inside of the other. Now, this inner sphere is going to have a radius that we are going to denote as Ri, while this outer sphere has a radius we are going to denote as Ro. Now there's a difference in temperature as well. There's an inner temperature, Ti, and an outer temperature, To. Now let's assign some values to our variables. Our inner radius is going to be set at 1 meter, while our outer radius is going to be set at 2 meters. Our inner temperature is going to be set at 100 degrees Celsius, while our outer temperature is going to be set at 0 degrees Celsius. Now the question we are going to ask ourselves is, what is the temperature at the midpoint? In order to figure this out, we are going to start off by writing our heat equation, which we know is Fourier's law. This is negative the thermal conductivity multiplied by the area multiplied by the change in temperature with respect to our radius in this case. And if we are going to assume that this is set at steady state, then we can say that this is equal to a constant. I'm going to denote this constant as Q, but you could pick whatever variable you'd like. All right, now we know that we have things in terms of our radius here, so we can actually change our area to be in terms of radius too, using the area of a sphere, which we know is 4 pi times the radius squared. Now plugging that into our equation, we get negative the thermal conductivity multiplied by 4 pi times our radius squared multiplied by the difference in temperature with respect to the radius equal to our constant Q. Now we can see this becomes a simple separable differential equation. So let's have our dT term, our temperature term on the left, equal to our constant Q divided by 4 pi times our thermal conductivity multiplied by our dr term over our radius squared. Now we can simply integrate on both sides. Notice I'm leaving out this Q over 4 pi k term due to the fact that that does not change with either temperature or radius. It is fixed. Now we must establish some bounds for this problem. Do we want our integral to go from the inner temperature and inner radius to the outer temperature and outer radius, or vice versa? Well, for this example, I am going to go from the inner temperature to the outer temperature, and to keep it consistent on the right side, we must go from the inner radius to our outer radius. Solving this integral, on the left, we will find that we will have the inner temperature minus the outer temperature is equal to Q over 4 pi times our thermal conductivity multiplied by the integral of 1 over r squared, evaluated from the inner radius to the outer radius, which we know that the integral of 1 over r squared is negative 1 over r. So right here, we're going to multiply our constant over 4 pi k times the reciprocal of the inner radius minus the reciprocal of the outer radius. Plugging in our values that I gave us, we're going to find that the inner temperature is 100 degrees minus the outer temperature, which is 0, is equal to our constant over 4 pi times our thermal conductivity multiplied by 1 over our inner radius, which is 1, minus 1 over our outer radius, which is 2. Simplifying further, we get 100 is equal to Q over 4 pi K multiplied by 1/2. Moving our terms over to the left and isolating Q, we'll get that Q, our constant, is equal to 200 times 4 pi times our thermal conductivity. Now back to our original question. What is the temperature at the midpoint? We can take our same equation we used over here, and this time, instead of evaluating from our inner temperature and inner radius to our outer temperature and outer radius, we are going to evaluate it from our inner temperature to our temperature at our midpoint and our inner radius to our radius at our midpoint. So let's write that out. Negative the integral dt evaluated at the inner temperature to the midpoint temperature is equal to our constant Q over 4 pi times our thermal conductivity multiplied by the integral of dr over our radius squared evaluated from the inner radius to the radius at our midpoint. Evaluating this integral, we are going to have on the left the inner temperature minus the temperature at the midpoint, which we are solving for, is equal to Q, our constant, over 4 pi K multiplied by the reciprocal of the inner radius minus the reciprocal of the midpoint radius. Now, how do we solve for our midpoint radius? Well, we can use the equation that the R inner, the inner radius, plus the outer radius divided by 2. This leaves us with 1 plus 2 divided by 2, or 3/2. Plugging in our other known values, our inner temperature is 100 degrees minus our temperature at our midpoint, which we are solving for, is equal to Q, which we established over here is 200 times 4 pi times our thermal conductivity, divided by 4 pi K, multiplied by 1 over 1 minus 1 over a midpoint radius, which we just found is 3/2. Simplifying this, we can see that our 4 pi K terms cancel, and 1 minus 1 over 3/2 is equal to 1/3. Here we're going to have 100 minus our midpoint temperature is equal to 200 times 1/3. Isolating to get our midpoint temperature, we're going to find that is 100 times 1/3. Or rather, our midpoint temperature is 100 over 3 degrees Celsius.